MOBISEC hackers, welcome back. I hope you had a nice week. And today we're going to finish up this series on Android system and security aspects. So yeah, we're going to keep focusing on some aspects of Android platform that are security related. And then from next week, we're going to change topic and we're going to focus more on the malware aspect and the vulnerability discovery aspect. Okay, so first thing I want to touch on today is, let me see if it's recording. It is the account manager. So what is it? So account manager, you have a link to the documentation, is an object, some kind of a platform provided abstraction that manages accounts in a centralized way. And the idea is that the user enters the credentials once per account, and after this, the user is basically logged in. Okay. The idea is that after this, applications can access online resources with one click without keep entering a username and password. And the idea, and this is actually how this stuff is actually useful, is that third-party apps can use existing accounts instead of creating new ones. Okay, so for example, you have Google, Facebook, I think also Twitter. These guys use the account manager and they create like an account in this account manager. And after you're logged in Google, Facebook, Twitter, and so forth, you're basically logged in these platforms and you're logged in this account. Again, account, I don't only refer to the web account of Google or of Facebook, I'm referring to an account entry in this account manager. Okay, and after you have this, basically now a third-party app, so an app that is not related to Google or Facebook, can actually rely on the creation and the account management process of the account manager instead of asking the user to create yet another account on this third-party app. Okay, so for example, if you have a game, you can basically show up to the user, hey, instead of creating an account with us, with the actual game platform, do you want to maybe log in with your Google account? Okay. Of course, in some scenarios, the game, for example, could even avoid to have their own infrastructure to create accounts. They could just have this Google or Facebook or Twitter related accounts management. Okay. So we're gonna dig a bit deeper in this. So for these account managers, we have authenticators, and these authenticators are basically these objects that validate account credentials and store account information. And again, each of these apps that create one entry in this account manager have their own authenticator. What they can do is to generate authentication tokens. And the idea is that once you have this token, basically this can be used to authenticate the request to the server without sending the user's actual password. Okay, so somehow the user puts username and password in this account manager. After this kind of entry in this account manager is able to generate valid tokens, and an application can just take one of these tokens, for example, generated by Google profile or the Facebook profile, to show to a kind of backend, hey, this user was actually logged in with the Google account or the Facebook account. Okay. And so the idea is that the app doesn't need to handle passwords directly. So even in the example of the game that uses Google account in a way to, instead of creating accounts for the game, this application never asks or never needs to ask the actual Google password to the user, because the idea is that the user is already authenticated with Google on the phone, and so there is a mechanism so that the app can just get this token from the Google authenticator and use the token to ask the Google backend, like, hey, is this user actually who claims he is? Is this token actually valid, and so forth. There is some kind of a relationship between this account manager and OAuth. I'm not sure you guys are familiar with this OAuth, so we're going to get a little bit deeper on this. So OAuth comes mostly from the web, web platform, but again, it's an open standard, and I think I copied this from Wikipedia. It's an open standard from access delegation, and it's used as a way for internet users to grant website or apps access to their information without giving them the password. Okay, so what is this in particular? Maybe you already are familiar with this. If you go to some specific websites, I think maybe on Medium. On Medium now you can say there is some kind of a pop-up that says, oh, do you want to log in with your Google account? The way it works is actually using OAuth. Okay, So concrete scenario, let's say the website X wants to avoid managing account creation or authentication, or it wants to avoid forcing users to create and manage a new username and passwords. That's where these things kick in, okay? So somehow the website X allows users to log in with their Google account. So website X, again, could be something like medium.com. And the way it works is that the app obtains Google authentication tokens from the account manager. And then with this token, it can prove to the server that, yes, I'm the user logged in as, whatever at gmail.com account, okay? The way it works under the hood is actually OAuth, okay? So this thing actually works with a web platform where basically you can do login with Google account on medium.com. What happens under the hood is that then there is some kind of a communication between maybe medium.com and Google backend, and so they actually ask each other, is this guy actually logged in with this specific username? And the idea is that the user is already logged in with Google, so he doesn't need to put the password again. Same stuff happens on the phone, and this example ties to this, how an app can actually use Account Manager to get access to these authentication tokens. And again, the idea is that it's nice because now the actual account creation, processing, password reset, all these things are actually delegated to Google. And some applications support both creation of accounts on that specific application, or through this kind of a third-party systems. But some apps are actually, you cannot log in unless you have a Google account, a Twitter account, and so forth. And again, it's not only the task of creating accounts, but it's also managing them. It's also trying to find frauds, try to combat that users could create a number of fake email addresses and so forth. Basically, all these problematics are now delegated to Google. Google already, of course, has system in place to prevent abuse, to prevent that you can script the creation of users or user accounts. Maybe they ask you telephone number, they ask you to solve some captchas and so forth, okay? So that's why this stuff is handy for third-party apps. Okay, switching topic, we're gonna focus on in-app billing. Pretty sure you are familiar in some way or another to this in-app billing. And now we're going to check how it's actually implemented and all the details on, all the different features that are available. So, in-app billing. So, it's a service that allows developers to sell digital goods from within their apps. Okay, and the idea is that users can pay to do a number of things, unlock extra in-app features. This could be a level in a game, or items in a game, or some content. It could be to hide advertisement. There are some apps that are very heavy on advertisement, and they ask you, you pay this fee, and then we're going to hide advertisement. And there are some apps that ask you, if you want to get more content, you can subscribe, and then each week you have a new episode or something. Okay. Now, from the technical perspective, it's not just, it's an interface to pay, but there are a number of things that we need to understand. First of all is that there is a concept of items, and these are the items that you can buy. Again, item doesn't mean it's an actual item you can buy from a store. It's an abstraction. Okay, this item could be additional content, additional level, or hide the advertisement token and things like this. So these items can be of two different types: consumable and non-consumable. And consumable, for these consumable ones, basically the user can own them and use them later on. And there are two possible states: either the user owns it, or it does not own it. And that's where the consumable work kicks in. Basically, I can buy an object, and then I basically can use it. Once I use it, I don't own it anymore. Okay, that's why I consume the object. And the user, if he wants, he can basically buy it again, and then you go back to the user owns it, and you can reuse it, and so forth. You can purchase it again only if it's currently not owned. Okay, so this means that if you have a game, and this game allows you to buy several items of the same type, probably under the hood they're handled with different types, because or with different specific items, even maybe if from the graphical user interface they look the same. Okay. The other type is non-consumable items. And once a user buys it, it's his or hers forever. Okay. Again, different game developers or different apps developers can implement their features based on one of these two. For some features, consumable may be the correct thing to do. For example, if you play Angry Birds and you have extra things to use, you can basically buy it. Once you use it, this item is not owned anymore, and you can buy it again, and so forth. So that's one way. For non-consumable things is one of these things that basically once you unlock it, is there forever. There is no concept in the game or in the app to use it, to consume it. Okay, this could be, for example, once you pay to unlock the advertisement-free version of the application. Another aspect of this in-app billing is that there is this one-time billing vs recurring billing. And one-time billing, it's these terms are probably you're quite familiar already. The idea is that the user pays once for each purchase, and it's a one-off transaction. Okay, recurring billing instead means that it's like a subscription mode. Basically, once the user pays, basically in the pop-up that says, okay, you're about to pay, there is also written you're going to pay once per week, once per month, yearly basis, how much is the amount, and so forth. The idea is that the user can stop it in time, and again, depending on what the app is trying to sell you, one of these two can be a good fit. Now, from the security perspective, and that's why I'm talking about this in-app billing, the presence of in-app billing is very important, because basically all these apps don't need to re-implement all these billing operations themselves. They can basically rely and delegate everything again to Google. So basically these checkout operations, the process of asking the user, are you sure you want to pay? The process of getting money out of the user pocket through some account and so forth. This stuff is handled by Google, in particular by the Play Store application. So the app itself doesn't need to ask the user, give me your credit card number and things like this. So the friction for the user is very low. There is a pop-up that is always the same from the Play Store. Hey, you want to buy X? Press a button and you're done. Okay. There is no other information that is requested from the user. And again, the other part is that not only the friction of the user is reduced, but also the complexity of these applications, because each app doesn't need to implement the logic of, oh, let me check with Google how much money the user have. Let me check with Google if this guy already has this item. Everything is handled through the Play Store. So basically the applications talk to the Play Store, and the Play Store then talks to the Google backend on behalf of the third-party app. And again, the idea is that this Play Store is developed by Google, and they take care of all the interactions, so the third-party apps don't need to re-implement this. And that's a great security benefit. Is also, of course, more practical. But again, security benefit should not be underestimated. We are talking about money. So, everything that relates to money or handling sensitive information, such as credit card numbers, can be a real pain for app developers. And so it's great that in-app billing is there. So in sum, the Google backend actually takes care of a number of things. And one is processing the payment, getting the money out from the user. And basically it takes the money and then it somehow puts them in the developer fund. For the developer to push an application on the store, you need to have a developer account. And basically you have a kind of fund where basically Google pushes money on your developer account, and then you can cash back or cash out. The idea is that the Play Store also keeps track of what's the purchase state for each user. So if the user changes application, if changes phone, either load the application again, as long as the user is logged in again with the same Google account, there is no loss of information. Okay. And so the app can query Google Play Store backend like, hey, is this user already in possess of this specific item? Did the user already buy this specific item? So you can ask these things. And that's good also because the user now doesn't fear that he's going to lose money if he changes phone. I buy object X. I'm kind of confident that if I change phone, as long as I keep logging in with my Google account, I know I'm not going to lose object X, which is good. Okay. Google also takes care of monitoring for fraudulent activities. And again, for example, there were applications asking crazy amount of money to the user, and that's not good. Sure, the user was informed, and maybe with some tricks, the user was convinced to buy it. Another trick was that basically you can offer some kind of a free period, and after this free period, you can start the subscription. And some people were crazy; they were doing, it's free for the first week, and then after the first week, you pay 200 euros. And the trick there was that you do the free thing and the user thinks it's free. And it's actually free because you can actually unsubscribe, if you remember. So some users were actually forgetting it, and then the 200 euros maybe was kicking in. Users were upset. So somehow Google tries to limit this kind of malicious behaviors. And it's a lot of work. And if Google wasn't doing this, then third-party apps, each of these third-party apps needed to do it. And that's not very pleasant. And that's why, again, this is not feeling great. In return, Google is not a charity organization. Google actually gets 30% out of the profit. This number, I think, is subject to change. I'm pretty sure this is still the number, but I remember hearing some deals that Google was doing with the big platforms. Because some of these big game developers, like for example the developers behind Fortnite, were quite upset because 30%, if you earn billions, that's a lot of money. But again, my understanding is that by policy, if you monetize something and your app is on the Play Store, you need to go through the in-app billing. Okay, so again, what I said is true. These are all great features, but also Google is not a charity organization. It's not that if you wanted, you can create your own in-app billing scheme. It's maybe possible. I'm not sure about the details, but I think there are a number of entries in the term of service that says that if you have an object that you can buy in the application, then it should be through the in-app billing system. Okay. I think there are some tricks maybe to bypass this, where basically some developer can have some kind of subscription on some website, so somehow it bypasses in-app billing, but I'm not sure how much Google likes this. And again, I'm not an expert in this in-app billing. I never made $1 on this kind of mobile apps. Cool. So from the technical perspective, let's dig a bit deeper in terms of steps. The way it works from the perspective of a third-party app is that a third-party app communicates with the Google Play Store through IPC, through intents, binders, and so forth. Okay, so you send an intent. That's how you communicate with the Play Store, which is another application on your phone. And whatever we discuss up to this point, it's relevant. You can trust security boundaries, and then you can trust that you're doing this communication with the binder. What kind of app you're targeting to. Google Play Store knows which kind of app is requesting the service and things like this. And the idea is that once you can talk to the Play Store, and the Play Store, once the app is ready to ask the user, do you want to pay? There is some kind of a checkout user interface, and ask the user confirmation about the payment. Okay, so the idea is that the user is already logged in Google, as it usually is, and then it's the same checkout UI for each of the kind of purchase, so the user already is kind of familiar with it, and there are all the relevant information, subscription mode, if it's one-off, if there is a free trial period, what kind of are the refund policies, if you can cancel it anytime, and things like this. Now, after the user pays or not, the application can obtain the payment status from the Play Store app. Okay, so you can talk to the Play Store app and you can ask, did the user actually pay for this? If yes, then you can unlock special functionalities and so forth. So, bunch of security aspects to discuss. The Play Store acts as a central point to handle all money-related aspects, again, which is very good. Otherwise, imagine if every third-party app would need to implement money management and credit card management, asking these things, and also there wouldn't be a nice centralized checkout user interface, so the potential for fraud would be much higher. The Play Store wouldn't have complete vision on what's going on the system, so it's also difficult. It would be also difficult for the Play Store, for Google people to say, this app is doing some kind of weird stuff. In this case, basically every transaction goes to the Google Play Store, which means it goes through Google. So Google has some kind of insights about what's going on, and you can take actions if some weird stuff is kicking in. So again, the pros: Google takes care of most aspects and is less likely to introduce bugs. You monitor frauds and so forth. The cons is that the app needs to talk to the Play Store. We have a well-defined interface, And then you may think, why is this a cons? Well, from the security perspective, the fact that there is a very specific interface through which an application needs to talk to the Play Store actually is a problem, because it makes reverse engineering much easier. And the idea here is that, if you need to have a third-party app that somehow protects, is the functionality to hide advertisement. Now, this app needs to ask to Play Store, hey, did the user pay for X? Since the interface that needs to be used is always the same, depending on the situation, it may be easy for the user to understand where this check is done. And if you could modify this application, then you may be able to bypass the check. And so you can always return, of course, user paid, and now you don't have advertisement anymore. Okay. So again, the fact that it is a very specific web interface, well specified and well-defined interface, great. But in terms of reverse engineering, it makes life much easier for the attackers. And again, basically the attacker may have a starting point to know when the app is actually, so when and how the app is actually using the in-app billing APIs. And the attacker, depending on the situations, could spoof the replies from the Play Store, faking that, yes, the user paid for this, and so forth. And the victim app can be tricked into thinking the user is actually paid, even if maybe no monetary transaction ever happened. There was some research paper a while ago where it showed that depending on the situation, some kind of attacks in some scenarios could actually be automated. And again, the automation was possible mainly because all these apps were actually relying on the same interface. So somehow you can build some kind of an engine that detects when this app is using these interfaces and modify the return value accordingly. There are other important aspects. One thing is that in theory, in-app billing could not even be used without the Play Store app installed. So if you don't have the Play Store app installed, you cannot use in-app billing. And again, in-app billing is implemented, the backend of these in-app billing APIs on the phone is implemented in Play Store. So without Play Store, it's tricky. But there are some kind of mod apps out there that somehow they support Google Play Store emulation, and they fake the things have been purchased. So the idea is that this app, you would some kind of implement a fake Play Store API, and then whenever you ask, did the user pay? Of course he paid. Google is not happy. One example was this Lucky Patcher. I think I checked it out maybe last year. I'm not sure it's still relevant. But the point is that there are these examples of automatic kind of applications that try to say, yes, the user always paid. And again, it's possible, or it's easy-ish, because there is a well-defined interface. Of course, Google did not enjoy this application, and so it is flagged as containing malware. Of course, if you go to this website, it was saying, Google detected Lucky Patcher as containing malware. Please disregard it. It's a false positive. Of course, it is a false positive in the sense that, I guess, it's not malware, but you may imagine why Google is not very pleased. Again, the point I want to make here is not specific to the in-app billing. The point I want to make here is that whenever there is some security thing that needs to go through a very well-specified interface, that's a potential for the reverse engineer to have an easier life. Okay, in-app billing is one specific example, but whenever there is a well-defined API, that's as a reverse engineer, that's where you maybe would start looking for tracing to understand what's going on. Maybe you can automatically spoof replies and so forth. Okay, let's see other things. A possible solution to this auto spoofer is that the server could check if this monetary transaction actually happened. And this actually works in the sense that the threat model or the attacker model is that the user maybe takes the application and modifies it. But if it's the web server that needs to check did the user pay or not, well, the attacker doesn't have access to the server. Okay, so there is a chance for the server to win this game. The attacker cannot reach that. The cons of this is that it really depends on the feature you're trying to implement. So somehow, if you can integrate the server, a web server, into the check, then first of all, it's more complex. That's a cons per se. And, depending on the fraud rate and so forth, you may not want to do it just because it's more complex. And, depending on the context, depending on the scenario, depending on the object you're trying to make payable, or, depending on which object you're asking the user to pay for, it may be very tricky to integrate a server in this kind of a framework. Why? Well, if it's a content that is unlockable and the content is already on the phone, then this, then the server, the server could say yes or no, but the content is already there. So the user, the application, the reverse engineer would actually see it. Okay. So this server is useful when the content you would unlock with paying is not embedded in the app. Okay. So if it's some kind of a subscription-based thing where basically every week there is new content, this stuff would work because the server will check, did they get paid? If yes, I'm going to ship new content to it. Okay. But if the unlocked feature, let's say, it's already somehow present in the app, then it's much trickier to integrate this kind of a server into the design of this feature. And again, this is not always applicable in all scenarios. And an example is, for example, if the feature you're asking the user to pay for is hide advertisement, there is nothing secret, right? The feature is that you're going to hide advertisement. So that means that the component to actually remove advertisement from the system, from the app, is already somehow in the app. So it's difficult to imagine a scenario or a design that before, asking, before deciding should I show advertisement or not, you're going to ask the server, the user, the attacker could spoof the result from the server. So unless the check and the shipment of the unlocked content all happens in the server, this stuff is not really practical. Okay. Now there is another cons. If you find a way to have this kind of a server-based check, there is still one attacker model where this could be bypassed, and that's the pay once, use everywhere attack. What does it mean? Okay, I think now I have more details on scenarios where you can actually integrate a kind of a server or an external server to say yes or no, the user paid or not. If you want to unlock additional content, maybe you can ship it after, only after the user said the user actually paid. And maybe the content is already on the application, but there is no, it's encrypted. And maybe the server will actually ship the decryption key only if the server could check, yes, the user paid. Okay. And it's not applicable, for example, if there is no secret to protect, example of this hide advertisement. And yeah, the other advertisement example. And because in this case, the attacker could just always modify the app to just not show advertisement. Okay. So I was mentioning before this pay once, use everywhere attack. And the way it works is the following. Basically, you buy the secret content. So again, that's a scenario where the content is not on the app, or the content is on the app but is encrypted and you don't have the decryption key. So you can pay it once, and then now you have the unencrypted secret that you just unlocked, and now you can copy it and distribute it around. This actually happens quite frequently. So there is some kind of a business model where I buy this secret content and then somehow I redistribute this at the discounted price. And again, there is a conceptual problem here. At some point, if you have some kind of an encrypted content or a secret content to be unlocked, the content must be decrypted on the device, which is attacker controlled. Okay. So, and that's, again, it's depending on the scenario, it's an open problem. One could use, various degrees of obfuscation to make sure that it's not that easy to isolate what is the concretely, the secret content you just downloaded. But again, we are entering a classic arm race. It's security through obfuscation. It could be quite effective for many people, but on the conceptual side, it's still a problem. If you have a subscription-based content, is much easier to protect. Okay, but again, the pay once, use everywhere attack, of course, works as well. You can download it once and then redistribute it. Again, if it's an audio file, maybe much easier to redistribute it. If it's some kind of a spatial component tightly integrated with the application, then it could be more complicated. Okay. Cool. Yeah, that's a yeah. Okay. So switching topic, I want to talk about some kind of a pattern that we have seen throughout the years, and that's the push that the Android security developers had to actually have a control system in terms of permissions, but not only, that is finer grained. So somehow you have this very coarse grained permission at the beginning. You know, if you get, you can do X, Y, Z. But now they want to ask you, are you really sure you want to do X? Maybe you want to do X, but not Y. So there is some kind of, that's what I'm talking about when I say finer grained control. So give the user more possibilities to express exactly what he wants the app to be allowed to do. Okay. So in other words, basically there is a push to refine existing permissions and mechanisms. Again, it's not only a permission, and this is a concept. Okay, it doesn't need to be linked to permissions or mechanism. It's a concept. There is this pattern of going towards finer grained thing. Okay, and I have 4 examples of different natures just to show what kind of a concept I'm talking about. So keep this in mind. And again, also outside the mobile security. So the first one is the control over premium SMS. There was this SMS, I mean, there is this SN SMS permission. Apps, if you have this permission, apps are allowed to send SMS without user interaction. And then, you know, the word is premium SMS, where basically you can send a message to specific numbers that will cause a huge, significant monetary charge to your mobile bill. Okay. So it could be significant and it could be recurring. So it is not that it's thousands of dollars. It could be, you know, maybe in the order of 2 to 10. But again, if you do this attack to thousands of people, then it's a significant fraud. Okay. And there are some legitimate use cases. Maybe, you know, if you are a follower of this popular Amici show in Italy, and you want to vote for your favorite singer, well, that's some kind of a mechanism to vote for them. If you have donations and things like this, that's the system that is used. Okay. Of course, people abuse this. There were at least very frequent premium SMS where, oh, you know, you send an SMS here and then every week we send you a new ringtone. This was popular, you know, 10, 15 years ago. And they would send you wallpapers and stuff like this, and every time they would charge you 3-4 euros. Okay, so people want to avoid this thing, and at least people want to make sure that, you know, when I say people, I mean the Android security developers, or anyways, the security people want to make sure that users are really aware about what they're doing. Okay, and so again, this could be a subscription model where you get money out every month, so it can be very painful. So there was this push of trying to fix the problem, trying to make sure that the user knows what he's doing, because there was actually malware trying to abuse this. Not only some advertisement convincing the user, please do this, but there was some malware that was getting this send SMS, and then somehow in the background was sending automatically premium SMS, and then the user would actually need to pay a lot. Okay. So in terms of security, a recent mechanism is that if the phone is about to send an SMS to a premium number, then there is a pop-up. Okay. And there is also new settings called use premium SMS services. And it's tricky, right? Because it's not that it's easy to understand if it's a specific number, it's one of these premium numbers. So the idea is that usually these premium SMS are behind these shortcodes. Shortcodes are these short numbers. And usually, you know, once you put your short number, like 5 digits, then there is some kind of a map that maps the short number to an actually longer number. And behind, you know, building this kind of map is not always trivial. Okay. So there are a couple of links that show the depth and you know, different problems in building this kind of map. So the problem of getting a given number, understanding if it's a premium number or not, is not super trivial. And so there are work in progress to make sure that there is a comprehensive list. And again, as I mentioned, in recent versions of Android, if you try to send an SMS to one of these premium numbers, you will get a pop-up like this, some kind of a, money icon and so forth. So at least the user has a way to understand what's going on. And again, this fits under this final grain permission, not because there are two different permissions saying, send SMS or send SMS premium. I mean, there is a new setting, so maybe it's also that. But the point is that, they somehow split the space in which you can use a specific permission. And then depending on the specific category you're in, maybe they take extra actions to make sure that you know what they're doing. All right, another example is the new install apps per app permission. I don't remember when it was introduced, maybe a couple of years ago, but for sure it was not in the original versions of Android. So the idea is that by default, you cannot install an app if it's outside the Play Store. And if you want to do this, so if you have a file that you want to push on your phone, or maybe if you download an APK, you want to install it, you cannot do this by default. You need to enable side loading. So side loading is exactly this: it's taking an APK and somehow installing it on your system, even if it doesn't come from the Play Store. Okay. And you can do this. You can go to settings, security, unknown sources, and so forth. And it was a system-wide settings. Okay. So once you click on this, every app on the phone can basically say, with the proper permission, can say, yes, I want to install this. Okay. The user is always asked, but without this, the user cannot even be asked. So the app cannot even prompt the user to install any application. Okay. But with this one, the app has a potential to do so. Now, okay, from Android 8, so 2-3 years ago, the permission is not system-wide anymore. It's handled on a per app basis. What does it mean? It means that each app that wants to install apps need to require this permission. And you need to enable this. It's called allow from this source, where basically you are telling Android framework, yes, I allow apps to be installed from this source, from this specific application. Okay. And there is a huge security benefit here, because now you can install apps from the Play Store, outside the Play Store, and still prevent malware to install additional apps. So for example, there are apps that are actually benign and they want to install other application, like you have third-party markets that are perfectly legitimate. The way that these apps are actually installed apps is that they ask the user, do you want to install this one? This app will not be part of the Play Store, and then the user will say yes, and the app will be installed. Okay. But let's say that the user has one of these legitimate third party. In the past, the user will need to say enable side loading, and now every other app would have a way to trigger and prompt installation of different applications. While in this case, the user needs to enable, it can enable just this legitimate app and not anything else. Okay. So again, that's what I'm talking about when I say that the permissions are being more fine-grained. Now we have from this system-wide, yes, you can select things. Now each app can say yes or no. Another example, ADB key-based authorization. So in the past, you want to play with ADB and attach the cable on your phone and get a shell. Well, by default, you cannot do this. But you can first of all enable USB debugging, and then in the past you could just attach the cable and get a shell from this ancient version of Android. Basically, ADB will create a RSA key pair, so private and public key, and then the authorization will be given per key basis. Okay, and without keys, this ADB is not accessible. So basically, at that point, you need to authorize a specific key in the phone. So if I am ADB and I say, hey, I'm the guy that has the private key associated with this public key. Can you please allow this public key to be used? The user needs to say yes. Okay. Without this, even if there is USB debugging, you cannot get access to the phone. And there is this trend of going from system-wide to per-use settings, where basically at some point, I don't remember which version, they changed, and now the prompt is, you are connecting via ADB from a computer, and the fingerprint of the key is the following. And now you can say okay, or okay and always allow. And that's great, because now I can say, okay, but it's not going to be allowing this forever. It's just for this specific use. And if I try again tomorrow, this stuff is not going to work. Okay, so again, you're having to finer grain control for the user to say, yes, I only want this specific thing, but I don't want to allow everything else at the moment. The last example I have, and again, there are several of these, is that I think last year in Android 10, they introduced the background access location permission. Okay, so somehow before there was, I want the location permission. Now the application needs to ask if, so by default, it doesn't have location permission if it's in the background. You need to ask whether you want to get the location permission also when you're in background. Okay, and so now basically the user would see something like this, where you have allow all the time, allow only while using the app, or deny. Okay, again, before it was just yes or no. Now it's yes, yes, but only if I'm using the app, and no. Okay, and again, it's some kind of a reactive way. There were applications that were somehow using location in background while maybe the user was not expecting it. I remember a case where I think the Uber app was, of course, using location while the user was maybe on the Uber, and it will show on the map where you are. But basically, even if you shut off the app, and even if the Uber drive is over, I think Uber was recording your location for a little while after the drive was over. Okay, is it malicious? No, in a sense that there was a use case. The use case that they wanted to track whether the driver actually left the user exactly where the user was supposed to be left. Because if the user, just enters in the house, then they know the driver did a good job. If the user needs to walk about a little bit, then they know maybe the user was, was supposed to left somewhere else. So they wanted to get inside about this kind of a thing, but people freaked out because it's not cool that Uber was taking this location information without telling user, you stop using this app, but we are somehow recording where you're going. Okay, so of course, depending on your, how much you value your privacy or the privacy of other people, then you may be upset or not. In my case, maybe I don't care. I mean, I care about privacy, but what I was pissed the most about this is that there may be scenarios where, for some specific category of people, this would be very, very sensitive. And I was pissed because this should be properly communicated. So the fact that it's not a big deal for me doesn't mean it's not a big deal for other people. And that's usually when I get upset. All right. So, okay, what time is it? Perfect. Another topic I want to touch. So basically, I'm done with this finer grain control. Please keep in mind, it's a trend. You're going to see this in future versions of Android. And again, I think it's an important aspect of how systems are developed. Is always some kind of a, there is a life cycle of this Android framework where they try something and then they say, there is a problem here. People are abusing this. Then let's fix it. Okay. Cool. All right, switching gear, talking about SMS and authentication tokens. That's a big, big trend, and it's very interesting. So the importance of SMS privacy is increasing. And in the past, it was mostly your private messages, very sensitive. But now, depending on the context, they are actually tokens. And these tokens are used to prove that you own a specific telephone number. And I guess you're familiar with this. Some application ask you, we send you a text with a code to your telephone number. Please let me know which is the code to prove that you actually own the telephone number. But there are some other cases where this token alone can give you much more power. And we're going to explore a little bit how these things work. So the usual step is that, to log into your account, you need to prove that you can receive messages at this telephone number. Okay, so the server sends an SMS to this telephone number, and the user receives the token, and he can put it in a website, and now the user showed, yes, I own this telephone number. Yeah, once the user puts it, then it's done. For some apps and services, this token is all you need to get access to the account. And if an attacker gets it, it's game over. So there are some accounts where the phone is used, this SMS token is used as a second factor authentication. But in some other cases, the telephone number is the factor to authenticate you. There is no username and password, and you know, if you get one of these tokens, then if an attacker gets one of these tokens, you may be in trouble. This is the case, or was the case, for WhatsApp, for Signal. Now, WhatsApp and Signal now try to push you to set up a PIN, so that once you receive a token, you put the token. Is not enough, you need to put the PIN. But my understanding is that by default, that's not the case, at least on WhatsApp. I could be wrong. Up to last year, it was not the case. And this means that if I can trigger a, you know, I'm logging in with a different, you know, I go to a WhatsApp that I just installed, and I say, this is my telephone number, and I put the telephone number of the victim. And if I can somehow get the token that the victim received, I can log in the WhatsApp account of this user. And again, this is getting relevant when the account, the telephone number is the account identifier. So the telephone number somehow is replacing the account name, the username, and the password. And there are a number of apps that follow this pattern. And there are some other cases where maybe the telephone number is not the only place. You also have the password, but in some cases, the telephone number access is the only thing you need to reset the password. Okay, so the severity of these attacks that somehow try to steal the SMS token can vary depending on the context. So there are a number of attacks. One thing is if you have physical control of your device. And one thing is that the attacker can steal the SIM card. If I steal the SIM card, I can put it in mine, do this kind of a bootstrap procedure, get the SMS on my SIM card, on your SIM card on my phone, get the number, and then I win. Okay, so for this kind of attack, I don't need to unlock the user's phone. I don't need to know the PIN code or anything like this. If the phone is unlocked, so if there is no PIN code or pattern or anything like this, or if it's locked but the notifications are not hidden, you know, for practicality, most people, what they do is to, you know, the phone is locked, but if you send me a message, maybe I'm gonna get a text and I'm gonna see the content of this message in the phone, on the phone main page before the lock screen. Okay, so either in these two cases, I can read the tokens, even if I cannot unlock your phone. So it's pretty bad. Another kind of attack is called SIM swapping, where basically you go to the telephone provider and you claim, oh, you know, I lost my my SIM. Can I have a new one with this specific number? And then you show up there with fake identity cards and so forth. Now you get the new SIM card, and now you can do the attack. The SIM card of the victim is getting disabled, and now the attacker can somehow receive these tokens and so forth. This is very, very popular, believe it or not. Another attack could be if you have a malicious app on the phone. And following slides are about exploring how a malicious app could be able to get access to these SMS tokens. So can I steal your SMS? So let's see. So first of all, a malicious app could ask the receive SMS permission and read everything. If you do this, then the app would receive all this SMS, and then somehow you will get the PIN and do all these attacks. Okay, it would work, but it's getting very hard to access this SMS permission. If you submit an app that asks for this SMS permission, there is some kind of a strict vetting, or, you know, maybe there is some kind of a human intervention that checks. So it takes a bit more time, and so arguably it's more difficult nowadays to get an app on the store that has this receive SMS permission. Is it impossible to get an app there with SMS receive permission? Of course not. It's just more difficult. Okay. Again, the bar is getting higher, but it's not impossible. The idea is that, you know, it is possible also because there are benign use cases that somehow want to use this, but there are also a number of you know, APIs and techniques that Google implemented or Android implemented so that app developers could implement this kind of a SMS-based authentication in a better way, in a more usable way. And that's where the trouble begins. Okay, so one thing is this SMS tokens autofill. Developers of popular apps want to make the process of receiving token and inserting token in app easier. Okay, so you not only want to use the SMS as the only factor, but you get the token, and then somehow the system needs to be able to understand, hey, this token is related to this app. Let me get this token to this application so that the app knows it without involving the user, without the user needs to scroll down, oh, this is my code, let me copy it, let me put it. Okay, so they try to push for some kind of automation. And that's where we talk about this autofill functionality. In the past, app would request this receive SMS permission, and then the app asks the server, please send me an SMS with this specific telephone number. Then the app would receive the SMS through the receive SMS, and basically the app would basically read the token out of the SMS and consider the user authenticated. Okay. But then maybe too many apps would actually ask for this permission with this specific excuse. So Google did something else. They created new APIs to receive tokens without SMS permission. Now, when I did these slides, this was last year. And at that point, there was 1-2 APIs. Now there are 3-4. And we basically have an upcoming paper with some colleagues at NDSS, where basically, we explore we do some kind of a security analysis of these 3-4 SMS APIs, and we show that each of these actually is not as secure as one would hope for, and then we propose some kind of a solution for it. But again, in these slides, I'm going to present some examples of what kind of problems we found, and then I'm going to have a link to the paper. So that's just to say it's in evolution, and there is a new API, there is a bug, Google has a new API. And the other interesting thing is that Google is keep putting APIs, which means that there is some kind of a pressure. Google really wants to fix this problem or making this kind of an autofill mechanism viable for third-party apps. So it's an interesting problem, and the various techniques are actually very interesting. So Google's solution was to introduce a new API to receive tokens without SMS permission. And the idea is the following. Basically, the app uses Android API to get an hash, let's call it X. And so the app actually asked API on the phone, hey, can I have X? Can I have an hash X? Great, now the app has X. Now the app sends X to the backend of the application, okay? And the trick is the following. If the device at any point receives an SMS containing the hash X, the SMS is automatically redirected to the requesting app. And you don't need any receive SMS permission, okay? And it's great because now I can implement this. I can basically ask my token as an hash. I get hash ABC. I send this hash to the backend. The backend is now sending me the two-factor authentication token or the one-factor authentication token to SMS, and it's going to put in the SMS the hash ABC. At this point, the system is going to receive this. And, there is hash ABC in the SMS. Let me redirect this SMS to the app that requested this hash and for which I provided as an answer ABC. Okay, this seems to looks great, but it's vulnerable. Why? Well, think about this. If you are on this specific phone and you have a malicious app installed and you have maybe the WhatsApp app that somehow uses this technique, what you could do is the following. The malicious app could initiate a procedure as well. Basically, the attacker could ask this API, can I please get an hash? Great, hash is DEF, fantastic. Now the malicious app send a message, or it contacts the maybe WhatsApp backend saying, you know what, I will need the second factor authentication token and my hash is DEF. Can you send it to me? WhatsApp said, absolutely. It's for some apps, there is no other authentication. This is the main authentication. So you're not already authenticated to anything. You just can communicate to the backend. So at this point, the attacker sends this, the WhatsApp says, yes, I'm going to send you the token, and it's going to put in the SMS the hash DEF. At this point, this message is received from the phone. The phone says, there is a hash DEF. Let me give this SMS to the application that requested this hash, which is the malicious one, and the attacker wins. Okay, so let me see if I describe correctly the steps in the slides. So you get an hash. The malicious app then sends the hash to the benign application backend. The benign backend sends the SMS containing the hash, and the framework redirects the SMS to the malicious app, and the attacker won. Okay? Believe it or not, this is an existing API on Android, and yes, it is vulnerable like this. Then they came out with a new API. It's called SMS Retriever. Again, this is the second one out of several. And yes, it's one of the main APIs. The idea is similar as before, but it's smarter in a sense that the hash they give you is somehow linked to the requesting application's package name. Okay, so once I ask an hash, isn't it I give some kind of a random hash, but I get an hash that is somehow linked to the application's package name. Okay, and then the idea is that it's done in a way so that the server can check the provenance of the request by, for a given hash, try to understand which package name, what is the package name of the app that actually requested this token. So if you are WhatsApp, you can ask for this, for this token, you get an hash. In this hash is going to be some kind of random hash, but it's going to be stored inside the fact that the requesting app for this token, for this hash, was WhatsApp, WhatsApp package name. If you had a malicious app, now the stuff doesn't work anymore, in a sense that if you get an hash, the hash is going to contain information that this is being requested by an application with package name attacker.evil. Okay. And so the idea is that once you send this hash to the server can check, what kind of package name requested this hash. Is it the one I expect? Yes, great. I'm going to send SMS. If not, then I'm not going to send SMS. Okay. But what if the server doesn't check? Then you're vulnerable again. And it turns out there were servers that, even if they could distinguish the hash is from this malicious app or unknown app, they wouldn't do it. They wouldn't check, and they would treat this as a normal hash and use it somehow in a way that was, that you would do in the previous case, where there is no, link between the hash and the package name, and you would be vulnerable like this. And again, I mentioned we have a new paper coming. It's going to be published in February, but we should have the camera ready, PDF ready sooner. And yeah, it's a study with some colleagues for the university that touches on checking all these SMS different APIs and checking which way they're vulnerable and whether we can do something better. Okay, so once I have the camera ready, I'm going to put the link in the slides. So there is going to be an actual link, in a few weeks in the slides. Cool. All right, give me a sec. All right, I'm back. So moving on a different topic, near field communication, or maybe you know it under NFC. Let's check it out. Super cool stuff. So NFC stands for near field communication. Surprise, surprise. And it's basically a technology that allows short range wireless communication. Short range means 10 centimeters or less. And NFC operates at this high frequency and 13 megahertz frequency and transfers data up to 424 kilobits per second. I think I stole this from Wikipedia. You don't need to remember this, it's just to give you an idea about what's going on, but it's not very, very fast. And the idea is that two devices can easily communicate one with each other. So the scenario is that you have two devices, you can put them together or near, and somehow they can exchange data. It's not extremely fast, but it's not that bad either. Now, there are a bunch of objects and entities, and when I was studying this stuff many years ago, I was a bit confused. So I'm going to try my best to systematize the different objects and entities that somehow are in the game of NFC. The other problem I found is that there are some resources online that use a number of different terms to mean the same stuff. So again, I try to systematize this. If you find different terms online, try to keep an open mind, try to map them to what I'm explaining here. If you find different terms, it could be that, something new, but something that maybe is similar to what I'm discussing now. So one entity or object is NFC tag. One is the NFC device. And then we have this NFC card with secure element and several others. So again, I'm going to try to do my best to explain what this stuff is all about. NFC tags. What are they? These guys are something small and passive. There is no battery involved. There is no power involved. And they can store a limited amount of information, and they could be rewritable. Okay. And they're very, very cheap. And they look like this, or they could look like this. So again, we're talking about small objects that you can put around and they can contain information. And there is no battery, there is no power, there is nothing else. They're passive devices. Super cool. But how do we interact with them? With an NFC device. So NFC device is actually more complex and it needs power. And there are 3 working modes. It can be an NFC reader writer, and you can play with these NFC tags or cards. You can be in NFC card emulation. Again, I'm going to explain what it is later on. And you can be in NFC peer-to-peer mode. Okay. So in terms of the first mode, this device to tag kind of a communication. As I mentioned, NFC tags are passive devices. There is no power supply. And the idea is that they rely on the active device to come into range to actually do something useful. So the cool magic stuff is that NFC device powers up the NFC tag via electromagnetic induction. So the idea is that there are some kind of coils in the device and in the tag, and the power device, the active device, somehow has some current going through the coil. This coil will generate electromagnetic field variation. This field is going to be picked up by the coil in the tag, and is going to generate a current in the or a signal in the actual tag. Okay. And that's how this kind of a communication can happen by this variation. Then the tag can reply back and say what's the content is inside. And that's mainly why device tags need to be very, very near. Otherwise, this kind of stuff doesn't work. Okay. So the second mode was host card emulation. And I was so confused when I was trying to read this at the beginning, because it was emulation of what? So it was quite confusing. And before explaining this, I'm going to try to introduce a couple of things that are important to understand what we are going to try to emulate with this host card emulation. So in the past, you had NFC cards and secure elements. What is, and these NFC transactions were mainly carried out using secure elements. Okay, so this secure element is an important aspect. And I have a very, very informal definition of this secure element. Is a piece of super protected hardware where you can securely store and access sensitive information. Okay, so it's a specific chip done in a very well protected way, so that even if you have a physical attacker that can get it, it's very difficult to understand what's going on inside and to tamper it and do power attacks and things like this. And again, you can trust it to be a very safe place to store sensitive info. And that's a more serious definition. Tamper resistant, so you cannot really tamper with it. Platform capable of securely hosting applications and their confidential and cryptographic data. Fancy words to say exactly what I said before. So very hardcore security chip with some sensitive content inside. And yeah, depending on the use case, they can contain sensitive info. They can also run code depending on the secure element. They have their own chip to actually run code. So extremely interesting and powerful devices. And the idea is that these secure elements are present in NFC devices or in SIM cards or in credit cards. Okay. So there are various standards that use this, and similar chips are now available in mobile devices. The main driving factor is mobile payments. So somehow you can store some sensitive stuff there in the secure element as you would store on a credit card, on a physical credit card. And now you can talk to the secure element and trying to get access to the information about the credit card. So all payment information will be stored on the chip. And this information will be impossible to be read or copied even from even by the device operating system. So even if you are the operating system, or if you're an attacker that compromises the operating system, there is no real API to say, hey, read from secure element. You cannot do this, okay? And this makes them very powerful place of storing information. The idea is that the chip would communicate directly with the payment terminal. So if you go somewhere and you need to pay, you have this payment terminal, and basically you can put your phone near, and and basically the terminal will talk directly to the secure element. The operating system just do the, if it's involved at all, just do the transmission of packets and so forth, but it's all, cryptographically encrypted, et cetera, et cetera. So, there is some kind of a secure channel between the terminal and the secure element on your phone. And it's very powerful, so that even if you compromise the operating system, you cannot read anything sensitive out of it. So again, in this case, the operating system really doesn't see anything. And if you compromise the OS, there is no problem. Cool. And now we go back to host card emulation. So before host card emulation, NFC cards embed a secure element. And NFC devices could only speak to secure elements, okay? So the operating system is not involved. It doesn't see absolutely anything. And, wouldn't it be great if these NFC things, NFC tags maybe on the phone or NFC device on the phone could do more than just interacting with these crazy sensitive secure elements? For example, maybe you want to have mobile apps that could store some info, and maybe there is a way to make them available to phones that are very near to you, okay? Or other device could ask your phone for some information, like, give me your contact information, things like this. And again, this content information, it's in the operating system, or it's on the Android framework or an app in Android framework, but it's not in the secure element. It's not very practical to put this sensitive, but not super, super, super sensitive information in the secure element, okay? So the idea here is that there is a bunch of information that is sensitive, but not crazy sensitive. And this information lives in the phone, like in contact applications, for example. And somehow it would be nice to extend this NFC mechanism that before host card emulation was only used for sensitive things like getting payment related information out of your secure element. So to make this thing available also to other to other less sensitive use cases, and that's where this host card emulation kicks in. So somehow this host card emulation enables a device to simulate a secure element. And somehow there is this NFC protocol that once it wants to talk, so by default, it would talk to maybe the secure element, so that's hardware-based secure element, but maybe there is a way to reroute some packets of this NFC protocol to the operating system instead, and now the operating system can decide how to handle this. So for example, if the question is, can I get your contact access, instead of taking this request and submitting this to the secure element, this will be, rerouted to the operating system. The operating system now can check, is there any app that has a contact information? If yes, then you get a reply. So now, if with this host card emulation mechanism, apps running on supported operating system can offer payment card and access card solutions without the need of physical secure element. And of course, this doesn't come for free, in a sense that if you compromise the operating system, then you could be able to intercept this kind of information, okay? So somehow you can imagine this host card emulation as a kernel space software. There is some kind of a channel from this NFC device to some kind of an app that wants to speak this NFC protocol, but they go through the operating system, and if you compromise the operating system, then the attacker wins. And but these things is okay for many use cases. It's risky maybe to support payments, but if the idea is to support share your contact information, if an attacker already compromised the operating system, he already has access to your contact information, so whatever, okay? So again, the fact that it could be compromised by an operating system doesn't mean that it's very bad, doesn't mean that we cannot use it. And actually there are many use cases for which we can actually use it. And there is a very active space here where other companies trying to fix problems associated with this. The third mode that I discussed before was the peer-to-peer mode, and one of the thing that was implemented in this peer-to-peer mode was this Android Beam. Somehow it allows a device to push end-of message onto another device by physically tapping the devices together. Very fancy stuff. So what is this about? The idea is to exchange contact information. This was one of the main use cases, where basically you take two phones, you put them together, and somehow they understand hey, we are in this together, peer-to-peer mode, let's exchange content information. My understanding is that this kind of a mode and this Android beam is falling unused, but for completeness, I'm here discussing it. The idea is that it's not that you put these two phones and then they exchange content information. There are some security guardrails to prevent abuse. For example, the sender app must be in the foreground and the receiving device, the data, must be unlocked, which means that if somebody steals my phone, they cannot just take my phone and put it on their phone and steal my content information. Why? Because the sender app must be in the foreground. And if it's locked, they cannot put the sender app in the foreground. Differently, let's say that there is a bug in the functionality that receives this data. I cannot just go around and then plug my phone, the attacker phone, on the victim phone and then somehow do this attack, because the receiving device must be unlocked. Okay, and if it's not unlocked, then I cannot do this thing. Then once you do this, there is some kind of a touch to beam user interface, and then it asks for confirmation. So it's well done. I don't think it's a security issue. Other use cases for NFC, you can have apps that can read from smart objects. So somehow you can put these tags in supermarkets, and then you go around with your phone, you can read what's the price of this and so forth, or some other specification, nutritional values for a specific thing and so forth. You can put tags on a poster, and maybe you can put your phone there and you automatically go to the URL of the project website, product information, and conceptually could be used for similar to barcodes. Okay. Then again, depending on the scenario, you may want to use barcodes like you do in shops or not. You can also use this for contactless transactions, where basically you have these terminals, this POS that reach out to your mobile device. And you can do this for assessing and ticketing, or to quickly exchange information across devices. Okay. So I think it's pretty cool technology. I'm not using it very, very often, but if I manage to use it with success, there is a sense of satisfaction and eliteness. Cool. So in terms of how this communication happens, and how from the technical standpoint, sure, there is some kind of a wireless stuff that we don't understand, and yes, we don't understand it. That's more for a Wi-Fi class and a wireless security class. But if you go on the higher level, we use the wireless and these fields to exchange messages. Of course, these messages use a specific format, and these messages follow the NDF standard. So NDF standard, it's a binary format, and there are these two things basically: messages and records. And a message can contain many records, so you have different levels of abstraction. And there are a number of APIs to implement functionalities related to this kind of NFC-based functionality. There is some kind of a tag dispatch system where the system scans for tags. So let's say that you take your phone and you scan for a tag. Now this tag has some kind of a content, and the system scans for tags, and if found, it analyzes the content, and then depending on some information within the tag, it sends this information to the appropriate app. So this data in the tag could include a meme type or a URI that identifies the data payload, and different apps can specify, what, I'm interested in this kind of URI pattern, or I'm interested in this kind of stuff. And depending on this, then the operating system says, okay, I'm going to send this message to this application or to this application. If an app is interested in getting access to NFC data, then, well, it's an intent filter. It's very similar to the pattern we've seen with if you want to handle specific URLs, you put an intent filter with action view, and then a specific intent filter specification with what kind of pattern or URL you want to deal with. Okay, so it's a very, very similar process. Here is some kind of an overview on how the system somehow decides where to forward the NDF message. And again, there are some technicalities. there is a link there. Is nothing super fancy. And some other notes on this security aspect. Usually, I mean, as far as I know, the user is always notified. So I think it's difficult to abuse it. And to start this NFC related communication, the device needs to be unlocked. So one of the potential threats you may have in mind is, oh, what if somebody gets near to my pocket where I have my phone? Well, if the device is not unlocked, then this stuff doesn't kick in. And the user needs to confirm, yes, I'm okay with processing this. So there is some kind of check that the user is aware about what's going on. The communication between these things is not encrypted. So if you are very, very near, then you can maybe steal some information. But of course, you can add cryptography on top of this NFC layer. Depending on your use case, you may want to do it. If it's just some product information, who cares? It's some kind of public product information. You don't need to have encryption there. Okay, so next topic is much bigger in terms of importance. And I need a sec. All right, I'll be back in a second. All right, I'm back. So we're going to move on exploring trust zone use cases. And we're getting to some really cool stuff here. Cool. So I explained and discussed trust zone in the past, and explain how basically it's you can have a CPU with two different modes: the non-secure world, where you usually live. So what we have explored so far, Android apps and the operating system, and then you have the secure world, where you have a trusted operating system and then trusted apps on top of this. Okay. And the idea is that depending on if the CPU is in the secure mode or not, you can access secure memory or not, and you can access some specific peripherals that are only available through the CPU if the CPU is in secure mode. In some different devices, the CPU is only in non-secure mode, and then you have a different CPU that is always in secure mode. So this is more a conceptual thing. As an abstraction, there is a secure mode and non-secure mode, and depending in which mode you have different capabilities. Okay, just a very, very quick recap of what we discussed already. And I've shown this picture in the past, where basically on the left, again, you have what we explored so far in terms of secure world and non-secure world. And again, normal apps on the non-secure world use space, and then our Android operating system with Linux and so forth. And then you have the trusted operating system on the right in the secure world, and trusted apps on top of it. And again, what I've discussed last time is that in your apps, there are some APIs that somehow expose functionalities implemented in the trusted world, in the secure world, from trusted apps. And I have a number of them. Here you can see them. I moved a little bit myself. You have the key store, DRM, fingerprint, and confirmation API. So the goal of this part of slides is to discuss in details how these specific primitives work, why they're important, and why they decided to implement them with support of trust zone. And again, the important point here is that these specific things are secure even if the Linux and Android OS is compromised. So these guys are these trusted apps are actually resilient even under very aggressive threat models. Of course, it could be that it's not that there is an attacker compromising your operating system. Depending on the context, it could be the user itself of his own phone that basically somehow tries to hack the operating system or tries to push a rooted version of the operating system and get root, maybe to access some privileged information. And even in this case, the user cannot do much. Okay. All right, so let's get to it. Some other more high-level things about trust zone. They are somehow referred with these T, trust zone execution environments. And again, conceptually, is a secure area inside the main processor. We talk about trust zone when we refer to the ARM popular implementation of T. So ARM is a family of processors, and these guys develop trust zone. And trust zone, we can say it's an implementation of a TE. So a TE is a generic thing, and then you can have different implementations. And Intel has another implementation of the TE called Intel SGX. Is different than Trazon. In Intel SGX, basically the CPU can start running in a protected mode, and there is no other processes can interfere when the code is actually running in this protected mode. And the idea is that the code running with SGX is very constrained. So for example, you don't have syscalls and you don't have things like this. So you can basically do computation and things like this, but you cannot do everything that you could do outside this protected mode, okay? And it is different, but somehow it falls under the same umbrella because it's a feature somehow allowing you to have some kind of a trusted execution environment. But again, there are different implementation and they explore different points in the design space. Okay, so since most phones run on ARM, and since most of these interesting APIs are built on top of Trazon, we're going to focus on Trazon. Trusty, it's another name that you're going to see around, is the name of the operating system running in the secure world. Okay, so on the non-secure world, we have Android and Linux. On the secure world, you need to have an operating system, right? Well, the one from Google is called Trusty. There are a number of components. The trusted operating system, so it's a secure operating system running in the T kernel space, and you have a bunch of Linux drivers to facilitate communication with this trusted app. So trusted apps are the apps that are somehow living in the user space of the secure world, and somehow they interact with their own kernel, which is trusty. And the idea is that now you have third-party apps like normal applications that somehow want to use functionalities of implemented in the trusted world. And so the way it works, as shown in the previous picture, is that you have the normal application. Somehow this application interacts with the operating system is executed on, like Android or Linux. And the idea is that this untrusted operating system then talks to the trusted operating system that somehow wants to talk in a way that it can talk to the trusted app. Okay, and so this is done by drivers. So the app can use some APIs, and then the Linux kernel has some drivers so which you can communicate easily with these trusted applications. And on top of this, there are Android libraries that facilitate the communication from user-led software to trusted API apps and vice versa. And again, there are a number of primitives that rely on this, and these are the ones that we're going to discuss next. So the first one is DRM. DRM stands for Digital Rights Management, and it's a technology to protect copyrighted or premium content. So the idea is video streaming. If you have Netflix uses DRM, and the way it works is that Netflix somehow downloads the good content on your phone, and then it displays this in a reduced format, like to fit your phone. But the danger that Netflix has is that the user would actually download this content, and now he has access to the full, high definition version and distribute it around, which is very bad for Netflix, right? So somehow they use DRM so that there is an encryption layer, and the content is shipped encrypted to the phone, and then it's somehow decrypted through the DRM, let's say, system, and this system actually run in the trusted world so that the user cannot really tamper with it. Okay, so the idea of this DRM is to make the user's life as difficult as possible, where the user in this case is not, of course, the normal consumer, but it's more a hacker that wants to somehow decrypt or get access to the raw stream downloaded from Netflix or any other platform. And again, DRM kicks in for this. So in terms of overview, you have the player application, which could be the Netflix, it could be any music application, and somehow there are a number of APIs that, some kind of media server and so forth, and then eventually you interact with this DRM management client, manager client, and this talks to an actual DRM manager service that somehow has access to the encrypted information, and you can ask for things, you can decrypt things, and so forth. Okay, but from the high level perspective, apps of course use high level Java APIs, which eventually inside them they use the DRM component, some of which part runs in the trusted application. And again, this brings me to this T-baked DRM, where premium content is decrypted with the help of these trusted execution environments. And the software running on the TE processor can access device-specific keys required to decrypt protected content. And these keys are not accessible even if you compromise the operating system. Okay, so it's very, very powerful. When there was no trust zone, normal system basically download things encrypted, and then they would try to decrypt it, and then they would show it to the user. And of course, they would try to do this decryption with a crazy amount of layers of obfuscations, so that the user, the attacker has some problems trying to understand, oh, that's where the stream, the raw stream is unpacked, and then I can dump it. But now basically people can use this T-baked DRM. So even if you compromise the operating system, then you still have a tough life. Okay, cool. And then there is a big assumption here, and the assumption is that users or attackers cannot run custom trusted operating system. If you could do this, basically you could flash your trusted operating system on your Android phone, and then you just instrument that one and the attacker is controlled there. So the assumption is that you cannot do this, and this assumption in normal modern phones, it is satisfied. You can flash a custom version of Android and or your applications, but you cannot modify the trusted OS or trusted apps. Okay, so it's the classic thing where maybe you can actually push it a new version, but it's all verified through verified boot, and so a trusted OS version that is not signed by Google or whatever manufacturer you have is not going to be run. So you cannot modify it. You cannot, in many cases, actually encrypted. Also, the trusted apps sometimes are encrypted. So it's pretty tricky. And, there is this assumption you cannot run code there, and this assumption is satisfied usually. Now, another thing, another one of these primitive that is implemented through trust zone is the key store. So let's get to it. So key store is a hardware-based key store, we can say. And the goal is to allow apps and operating system to store cryptographic keys in a container that makes it more difficult to extract them. There are a number of security features. Keys are created unexportable. What does it mean? It means that there is a primitive, an API to create a key X, but there is an API to use key X, but only the owner app can actually do it. But there is no API to actually extract key X. Now, it would be very difficult to implement an API like this without trust zone, because you can implement this at the operating system level. But if an attacker actually has access to the operating system and it can compromise it or can flash a custom version of it, then the attacker could modify it so that now it's exportable. So you could actually see the key. But in this case, these things are actually backed by trust zone. So it's a hardware-based, hardware-backed key store. And through this trusted app trick that the user cannot modify, you can have an implementation like this, where basically you create a key, but the key lives in this trusted area, and then you can use the key. But again, the device or the component that does the decryption or the encryption or the signature is actually in the trusted part, so you cannot see what kind of input it's operating on. This happens all in the trusted part, and there is no primitive to say extract. So this key lives there and is going to stay there. So even if a malicious app gains full control of the operating system, or if the user wants to somehow hack his own phone to get keys created by some kind of one of his own applications, he's going to have a tough time, because you cannot get access to the key. Depending on the situations, however, you could actually use the key X through one of the primitive, the second primitive listed above, but at least you cannot really read it, and in some cases this is going to make the difference. So you can use the key, you cannot access this value. Again, I'm gonna discuss a couple of scenarios where this stuff actually matters, and that's it. Even if an attacker has physical access to the device, he's going to have a tough time to actually extract the key, okay? Because these keys are actually backed by hardware, and they're usually, backed by sophisticated hardware that is protected from a number of attacks, including physical attacks. Okay, so it's difficult to tamper with it. It's difficult to do some kind of a side-channel analysis, power analysis, and so forth. And so even if you steal my phone, it's very tricky for you to read and to get us to this kind of keys stored in the hardware-baked key store. Now, another thing is that the app that creates the key can specify how the key should be used. Okay, so it's not just that I create a key and then I can just use it, but you can specify other kind of a characteristic. And again, depending on how you do this, you have different interesting properties. So for example, you can specify what kind of algorithm you want to use, what kind of operations you want to support, what kind of purpose, what kind of padding scheme, if it's a block mode, if it's a kind of digest. So you can set up, you can customize the key the way you want. You can also define the temporal validity interval. So after a certain point, the key, you cannot use it anymore. And again, depending on your scenario, this may be a useful thing. If something is supposed to be a one-shot thing, you want maybe to have an expiration for the key. And then it's interesting that you can say, basically, it's okay to use this key, or you should allow the requesting app to use this key only if the user was recently authenticated. Okay. And this brings me to this topic where basically we have this key master AHL, this the hardware abstraction layer, and the key material may be bound to the secure hardware. So there is the key store and the key master, and then you have some kind of primitives, and then you could have some key master implementation that are not backed by hardware, and you may or may not have some kind of a hardware baked key store. In our case, the one we are interested in is actually T baked and secure element based key store. And yeah. So, and then from recent versions of Android, you have this Strongbox keymaster, which is an implementation of this keymaster hardware abstraction layer that uses hardware security modules. Okay. So in recent APIs, you can have this interface. Sorry, in recent version of Android and devices, you have this keymaster interface, and you have some guarantees on how it's implemented under the hood. And in this case, the security module has its own CPU, secure storage, and a random number generator, and so forth. So it's quite powerful. So the API can actually be very confusing. So pay attention if you are going to use it in the future. Hardware can be used to secure crypto keys, but that's not the only role of hardware. So, for example, I found this interesting question on Stack Overflow, where a guy that actually knows a lot of Android asked what was the difference, or was confused about some of these APIs. And for example, there was this API is inside secure hardware, okay, and there was is user authentication required, okay. So I guess you get the idea here. Is inside secure hardware. Maybe it's like, is the key actually stored in the secure hardware? For the second question, to use the key, does the user need to authenticate? So is the user authentication required for me to be able to actually use the key? And then there was something like this, where it was, is user authentication requirement enforced by secure hardware? And then you can think, what is the difference between this is inside secure hardware and is user authentication required enforced by secure hardware? Well, believe it or not, the last one is not related to where the keys are stored. If you actually read carefully what's written and the name of the API, you get it. But I personally was extremely confused when reading this. You can see the comments in the Stack Overflow link. But the idea here is that one thing is that the hardware somehow stores the crypto material. And the second aspect is whether the authentication requirement is enforced by secure hardware. Okay, because if you think about this, what does it mean the user has authenticated? It could be the user put some password. Well, this could, you don't need to, there are many implementations that don't rely on hardware to implement this. So maybe if the operating system was compromised, it's very easy to simulate that the user actually authenticated. But in the case where the authentication requirement is actually enforced by secure hardware, this stuff is protected even if the operating system is compromised. So the hardware is actually useful to protect and to establish whether the user actually authenticated or not. Okay, I'm going to have an example about these kind of keys in later slides. So if you are a bit confused, hold on. The later slides are these ones, the fingerprint API. Okay, so the fingerprint API is extremely interesting and I'm a big fan of it. So what is it? It's an API that allows an app to ask a user, please authenticate yourself using the fingerprint sensor. Good. The way it works is that once you do this, there is a callback that is invoked. So as an app, you can register a callback. Once the user is authenticated, you get a callback, and the callback says, yes, the authentication was successful or not. And so the app knows if everything was fine or something went wrong. The interesting part is that the finger API goes beyond asking the user to touch the fingerprint sensor. And it's not just I asked this, but it can be linked to cryptographic material, and that's where the link is with the previous topic. So the idea here is that, okay, before I touched on this cryptographic API, this cryptographic link with cryptographic material, one important point is that in modern devices, the fingerprint API is actually implemented in Trustzone. Okay, so the part that reads your fingerprint and manages it and says yes, it's actually implemented in Trustzone. Okay, cool. That's very important. So now back to the cryptographic material. Somehow the fingerprint API allows apps to create cryptographic keys that can be unlocked only when the user authenticates herself with the fingerprint. Okay, and this is one instance where not only maybe the key is stored in hardware, but also whether the authentication is hardware based, and the fingerprint is one of these. Okay, so these keys are made are T-baked and they are unexportable, as I mentioned before. So it's the same as the Keymaster API. And they can be created in two ways. Again, this part is now about this fingerprint API. They can be created in this encrypted decrypt mode or signature mode. Let's get to it. So encrypt decryption mode. The idea is the following. The key is created within the trusted execution environment. And the key can be used to decrypt only when the user authenticates herself. Okay, so we said before it cannot be exported. So I can create the key, but I cannot read it. But there is an API to actually say, can you please decrypt this secret blob that was encrypted? Okay. So the use case could be that the app encrypts a user's secret with a fingerprint protected key. Maybe this secret is there, some kind of encrypted password, something like this. And basically, the decryption key lives in the key store, lives in the hardware. Okay, so if an attacker is able to compromise the operating system and to read this encrypted secret, still he cannot do anything, because the only way to enable Trustzone to use the encryption key or the decryption key is from the user to put the fingerprint. Now, of course, if you convince the user to put the fingerprint, of course the attacker wins. But if you just steal the secret encrypted, you cannot do much. And again, maybe the app that wants to use this encrypted secret, then it needs to ask, can you please authenticate? You put the finger, okay? If the fingerprint check is successful, then the app can now use the Train API, the crypto key, which is now unlocked, and decrypt the secret. Now, depending on the scenario, this is good, but this also may not be the best way of doing this. For example, we worked on a paper in the past on this specific topic 2 years ago, and one app that we identified was 3 years ago, and one app we identified was Square. Square is this mobile payment app, and they were using the fingerprint API to ask the user, hey, do you want to, are you okay in sending this money to this other person? They will say yes. Now, I think this is pretty secure, but conceptually, if the phone is compromised, so if there is another application that got root, can this attacker, send arbitrary Square transactions around and authenticate them all? So it depends on how it's implemented. In this case, Square implemented this with this mechanism. So it was fingerprint API with the crypto mode. So somehow the user logs into Square, and then there is some kind of token. And then for each transaction, the user will be asked, hey, do you want to authorize this? You press the fingerprint. At this point, the app has access to the crypto key. Sorry, he can use the crypto key in the hardware to decrypt the encrypted token. you can do this because the fingerprint was correct. And after you decrypt this, then you have the unencrypted token, and you can use this to authenticate. So you send this to Square backend, and Square backend knows, okay, this is the real token, so the user said yes. However, if the attacker actually compromised the operating system, the attacker can just wait for the first instance of this transaction and can read the unencrypted token. So again, it's important to understand that the key is going to live in hardware and you cannot read it. But if you have a secret encrypted and then you want to decrypt it, the decrypted version of the secret is going to live in the non-secure world, maybe on the operating system part, but it's a non-secure world. So if the attacker compromises this operating system, the attacker is also going to see the unencrypted version of the token. And we actually communicated this problem to Square, and then we had some discussions. Then nothing much happened. But conceptually, the interesting part was that there is a way to do better. There is a way so that even if the attacker actually compromises the operating system, you cannot steal the token once or wait that the token is used once and then keep using it. How do you do this? With the sign-in mode, with the signature mode of the fingerprint API. So the way it works is the following. NAP creates a for signature key. So again, it's a different mode. It's not encryption, it's for signature key. And the private key lives in the trusted execution environment, and it is unexportable. Then there is the public key, which is public, so you can actually export it. So now you have an application that creates private key, public key. Private key lives only in Trustzone. Public key also lives in Trustzone, but you can export it. So the app now has the public key. And the idea is that a valid fingerprint now would need to, be used to sign a message with the private key. So when you are in this sign-in mode, the API that is available with the fingerprint is, I would like to sign this message with the private key that we created before. And could you please do this? And at this point, the user sees a pop-up, and the user can put the fingerprint. If the fingerprint is correct, the message is signed with the key that was stored somewhere in hardware. And at this point, basically, the receiver of this message, which is signed, can verify that it was signed with the correct key, because you can always take the message, text the signature, and then use the public key to verify it's correct. And so at this point, the app can verify, or the app of the backend can verify that the signature is correct using the public key. I have an actual diagram here to show this use case, again, with the idea of, for example, online payments through applications. So imagine a mobile app that wants to authenticate each monetary transaction in a way that as a malware, you cannot just wait for the first one, and then after this, you can replay everything, but in a way that the malware cannot do much, even if this is a successful authentication. The setup is the following. First of all, you create a private key S and a public key P via the fingerprint API in signature mode. And then you take this public key P and you send it to your network backend. And now the network backend approves transaction T only if it's signed with S. Okay? So the backend can verify, okay, this is a correct signature because it verifies against the public key P. And at this point, the backend can say, okay, I'm going to authorize this money transaction. Okay, it is safe because the key S is unlocked and can be used only with a valid fingerprint. Again, unlocked doesn't mean exportable. Unlocked means that now you can use the API, please sign. Okay, and it's usually one shot, but you still cannot get the actual content. I also have some diagrams. So let's say you have an application, and let's say you have a network backend. And let's say that now use this fingerprint API to create a new private public key in signature mode. So you're going to create these two things. And these are going to be somewhere in Trustzone. Then the idea is that once you create the account, you can send the public key, you can send it to the network backend. And then at this point, after a while, the user wants to send some money. So you say, okay, let me send some money. And then he says, I would like to pay $10. And then the network backend, okay, great. But before doing this, I need to know that it's really you, and that is not just a malware impersonating you, or not just a malware starting these transactions. So the network backend can ask the app, all right, sure, but can you please sign this specific token? At this point, the user is asked to use the fingerprint. The user puts the fingerprint. If it's correct, the key is actually unlocked, this private key, and now the app can use the primitive to say to the fingerprint API, please, can you sign token XZA whatever with the private key? Great, and now you can send it back. And now the network backend can use the public key to verify that this token was properly signed, at which point it can say, okay, authorize the transaction. The beautiful part of this is that even after this transaction, basically the malware cannot just replay this, because the next time there is another, if he wants to initiate another transaction, there is going to be another token. He would need to resign it. Hey, but how can you resign it? The key is always in trust zone, and to use it again, you will need to put the fingerprint again. Okay, so you see how how it's much more difficult for an attacker. Okay, so very, very cool. Yeah, key S never leaves trust zone. Now, some more info. There is the documentation, and this is the paper I mentioned before. We studied the different ways of using the fingerprint API and potential problems. And it's a recent API, and it's already deprecated. So there is this thing called biometric prompt. And so I think Android wants to push to this more generic biometric prompt, where basically you have some similar APIs, but instead of focusing on fingerprint, it could be based on the fingerprint, based on your face, and so forth. Turns out that in Pixel 4, that was the most recent phone at the point when I did the slides, there is no fingerprint, and there is just face recognition. And I mean, it's not very good. I mean, I'm not a big fan. I'm a big fan of this fingerprint because I just take it out of my pocket and I already have the finger there. So when I have it in my hand, it's already locked. Tons of problems and issues with this face recognition during COVID pandemic because people wear masks and this guy was not unlocking. I mean, rightfully so. So this is a personal opinion, but yeah, they were transitioning to this face recognition and using this biometric prompt. And unfortunately, on these phones, apps that were using this fingerprint API were now broken because there is no fingerprint anymore. And of course, the fingerprint API, maybe you can use it in terms of is the API there, but of course, it doesn't fly. Now, one of the latest last topics I have for today is attestation. It's extremely interesting technique. And before explaining what it is, I would like to explain a problem, and then I'm going to show how attestation solves this problem. So attestation tries to answer the question or whether you're actually speaking with the real trusted execution environment. So for example, you send me a public key. Imagine the scenario before. I have the mobile app sends the public key. But how can I know that you are a real trust zone execution environment or trusted execution environment? It's just a public key. And locally, the security is enforced via hardware. So somehow, if you are locally and you use some kind of a trust zone-based APIs, you have some guarantees. But when you send things out on a server, how can the server trust what's receiving? Locally, again, only the TE can access some keys. But if you are trying to compute some information and send it, then you have troubles, okay? So whenever you have a remote component, you may be in trouble, and maybe that's where attestation kicks in, okay? So how can the server know it's talking to a real TE? And in some cases, the remote component must know that it's talking to a real TE. So there are scenarios in which being a TE, talking to a TE, great. Not talking to TE means everything is compromised, okay? So there is this need for a remote server to understand, who am I talking to? Is it the real thing or not? And again, this is relevant for the fingerprint API. Let's go back to the example and let's see how it's vulnerable. So let's say that the attacker kicks in not after a while, but at the very beginning. So let's say the attacker is already there once a user is logging in for the first time, and the attacker is already there once the application is trying to create a private public key. The normal app can actually do this. The app is going to create a private public key, and they are locked in trust zone. And in the previous scenario, you have the app that is actually sending the public key to the remote network backend. So the attacker cannot really attack this private and public keys. Okay, because they're actually hardware baked, and the attacker doesn't win. However, there is still something that an attacker can do to fool the system. What is it? Well, one trick is that the attacker could stop this part. So, he stops. There is no public key being sent to the remote network backend. What the attacker can do is to create its own version of private and public key. These are just keys, and of course, they are not in trust zone. The attacker creates them outside, and the attacker has access to both, also the private key. And at this point, the attacker sends the public key, the P prime, to the network backend, at which point, it's actually very easy to forge transactions. The private and public key with trust zone are actually secure, but if all it needs is to sign things associated with the public key P prime, then the attacker can do it. Okay, so the attacker can forge any signature and he wins the game. This is a term from the paper. It's a nice term, but it's nothing official. We call this kind of a threat model attacker bootstrap, because this works only if the attacker is there from the very beginning. If you're already a user of the mobile app and this bootstrap is already been done, then you cannot really tell the network backend, hey, please forget about the previous public key, but use this one. If you could do this, then of course it's relevant, but this would be yet another assumption. So this attack is not particularly practical, but it's actually very interesting because it shows that without a system that tells me, is this key trusted? Can I trust this key? Then it's very tricky for a network backend to fully trust what's going on the other side. And again, that's where attestation kicks in. Attestation is able to solve this problem. So the idea is that a remote component can verify or attest that a given public key is T-baked and thus secure. Okay, so it's some kind of magic primitive that given a public key, I can, through attestation, I can say, let me check it. Yes, this is actually a key generated from trust zone. Since I know it's generated from trust zone, I know that the private key still lives in trust zone and is safe. The attacker cannot have access to it. Okay, so how does it work? The idea is that these keys are assigned. So you have a public key from these, and these keys, I know it's a bit tricky, but these guys are also signed, and they're signed with the hard-coded key that we call root trusted signing key. Okay. And how can we trust the root key? Well, the manufacturer places it there. So on your phone, there is trust zone, and then there is some kind of a key that lives in hardware and has been there from the very beginning. And it's another instance of this root of trust and chain of trust. Okay, so somehow there is a key on your trust zone implementation, physical implementation, and the attacker cannot actually have access to it. And then it's a key that we trust because the manufacturer places it there, but I cannot just come up with another root key. So if I can try to create my own root key, if I send it around, nobody's going to trust it. So there is a way to somehow understand, hey, this root key was actually generated from something that is trust zone. And again, it's done with this chain of trust kind of thing that we've seen already with SSL, with all these certificate chains and so forth. But the idea, again, is that I receive a public key which is signed, and by verifying the signature, I know this public key was generated from a trust zone component, a real trust zone component, and not by an attacker. Okay. So, and this would defeat the attack I presented before, because now the attacker could still generate a private and public key on its end, but once he sends this public key P prime, he cannot really fake the signature, showing that it's really coming from trust zone. Cool. And this is my last slide for today. It's ID attestation. It's a variation on, attestation is more, it's a generic concept. And it's like when I want to convince a remote component that, hey, this is really trusted. What we've seen so far was, yes, I generated a public key, and yes, this public key was generated in trust zone, so that private key, don't worry, is actually safe. The other topic of attestation that we've seen today is ID attestation. What is it? Somehow it's a mechanism that allows a device to provide proof of its hardware identifiers, such as serial number or IMEI. So let's focus on IMEI. Let's say there are some scenarios where the app sends an IMEI to a remote server, and then the remote server wants to make sure that this is the real IMEI. It's tricky, right? Because an application, an IMEI is just a number. So an application can just come out with some random number, send it to the server. How can a server know if this is the real IMEI? is tough. Idea attestation comes to the rescue. The idea is that once the phone is produced, is created, there are copies of the device hardware identifiers that only the TE can access before the device leaves the factory. So before the device leaves the factory, they actually code this information in hardware, and this information in hardware is only accessible by the TE. Okay, so then the IMEI is replicated somewhere else, so normal application can actually access it without big problems, but there is a copy of the real IMEI somewhere accessible by trust zone. And the idea is that the user could try to unlock the device, change the bootloader, but change the operating system, change everything, and change also the IMEI, but the TE-based copies of the IMEI are there. So I guess you get the intuition. The intuition is that the trusted execution environment can get access to this trusted IMEI, then you can sign it similarly to what we did before, then you can send it out, and now the receiver, the remote backend says, okay, this is IMEI, and there is a signature. This signature comes from a private key that is somehow leads to eventually being generated by a real trust zone. Since it's a real trust zone, I know it's not an attacker trying to fake IMEI, so I know it's a real IMEI, and so I can trust. Okay, so it's extremely powerful technique, and it's one of these things that you send something out to a remote server, and somehow the remote server is able to know this guy is tricking me or this guy is not tricking me through this kind of a authentication chains. Okay, so that's okay. Last point. Yeah, your phone can prove to a server that that's your IMEI or serial number. So I'm not sure these APIs are actively used, but they're there, and it's actually very, very cool. I think this could be used for from safety net. So maybe some of these APIs from Google to acquire information about the phone, and then this information is sent out. It could be that safety net is getting this info using this ID attestation. I mean, it's very, very cool. It's been around for at least one year and a half, or 2 years. So I would be shocked if they don't rely on these ID attestation tricks. Okay, so that's all I have for today. And yeah, enjoy the rest of the week. Let me know if you have questions. Even if you see this video, and you're not in the MOBISEC class, you are from the public, when I'm gonna make this video available, please shoot me an email. I'm always happy to receive emails from students around the world. And this is the last slide deck on topics on system security. And from the next week, we are gonna focus on malware and vulnerabilities. Enjoy the week again, and I'll see you next time.